Welcome to our practice problems looking at interactions in 3D, materials from chapters 10 and 11. So let's start with a simple question, or not a simple question, but a geometry question. What's the matrix that reflects a vector around the plane x1 equals x2? Given that you've computed that matrix, assuming you use it to map the unit cube, what's the volume of the resulting parallel pipette? So what's the volume after the map, and what is the map itself? Work on that and come back to the video after you've figured out what your answer is. Okay, so as we move from 2D to 3D, the solution for many of these problems can often be simple. Since this is a problem that involves only x1 and x2, the last component, the last column and last row are just 0, 0, 1. We're not actually working too much on the third dimension, and then we just get a reflection, the standard reflection matrix for 2D for our upper left-hand side. So that's how we can easily build our reflection around that particular plane. More complicated planes are more difficult, but for many of them we can solve it in reasoning from 2D. Since the determinant of this is -1, if you can't remember how to do the determinant, copy it over, do the determinant calculation. I'll show you that in a second. But since the determinant is -1, the unit cube started with volume 1. After mapping, it's going to have volume of -1, which is change of the direction. Okay, coming back to how to do the determinant, again, just a reminder, we're just going to take 0 times 0 times 1, which is 0, minus 1 times 1 times 1 is -1. And then we're going to take 1 times 0 times 0, which is 0, minus 1 times 1 times 0, which is 0, and then 0, 1, 0, which is 0, minus 0, 0, 0. So our overall determinant is just -1. Most of them were multiplied by zeros and went away. Okay. If that one was a little challenging, we'll make this one a little bit easier. What matrix rotates around the E1 axis by alpha degrees? Again, work out your solution, come back after you have it. So at least for me, the hardest part of remembering these is which axis is going to have the ones and zeros and which one's going to have the cosine. Again, since the E1 axis doesn't change, we're rotating about it, so it's the one that doesn't change. The first component in the first row of the matrix will be 1, 0, 0 and 1, 0, 0 transpose. So our matrix is take the dimension we're not going to mess with and then put the cosine alpha minus sine alpha, cosine alpha, the standard 2D rotation in the other part. If we were looking for any other dimensions, say we wanted to rotate in R3, we'd put 0, 0, 1, 0, 0, 1 in the last column and last row, and then put the cosines over on the sides, on the upper right-hand side. So basic axial rotations are relatively straightforward. Now let's go to a much more complicated problem where we're going to put some pieces together. We're going to break it down to two parts. What is the matrix to shear parallel to the E1, E2 plane? And then describe how to shear along an arbitrary plane that goes through the origin and has normal n. Ignore this. So hopefully you've got your answer now. If we start with the assumption, because we're going to start with E1, E2 plane, then our skew transform has the elements S1, S2, and 0. So we put into our shear matrix is given by 1, 0, S1, 0, 1, S2, 0, 0, 1. This is going to give us our transformation to basically shear because we're shearing along the E1, E2 plane, we're shearing this last column. Okay. In order to consider an arbitrary plane, that is any other plane that goes to the origin, we're going to rotate it such that the E3 axis is rotated to have the desired normal n. So you find some way to rotate it, shear it with the above matrix, and then rotate it back. In fact, this is the easiest way to figure out a general shear is rotate it so that you're in a known axis, shear it, and put it back. Figuring out how to do the rotation is a little bit more complicated for many problems, but this simplifies the whole process. Okay, so now let's look at some properties of these matrices. Find the inverse for each of the following matrices. First is this rotation, the scale, and the projection. This should be pretty easy, so I won't give you a lot of time. You should just be able to answer this without having to go back to the book. Okay, so for rotation matrices, you should just remember that rotation matrices are orthonormal. Their transpose is their inverse. So all we have to do is transpose it, which is just flipping the sign. Again, thinking of it in terms of physical things, if I rotate by 30 degrees and then rotate back by 30 degrees, I get the identity matrix. Our rotation matrix does exactly that. And that's just because sine of alpha and sine of minus alpha are just negating their sign, the sign in front, so these two change their signs. Now for scales, it's also very simple. Scales are a diagonal matrix. So for any diagonal matrix, we invert it by just taking 1 over the element. And remember that we only do 1 over the element if it's a diagonal matrix. For the projection, nothing exists. You can see that because this has got all zeros on the bottom. So the matrix is singular, meaning no inverse exists. In fact, all projection matrices have no inverse. They've lost the dimension when they do their projection. Okay, now let's try and go the other way. Let's give it a matrix, try and figure out what it does. So here's a matrix, given a linear map given by this matrix. See if you can figure out how to describe in words what it does. As usual to approach this, you might try a few examples of getting a feeling for what's going on, and then see if you can come up with the general form of what it does. You might look at things like determinants to help you understand it. Okay, so hopefully you've looked through that and come up with what you think is your answer. So first, I like to start with just figuring out what's going on with it. So this has a determinant of this matrix. You go through the determinant process, has a value of -1, indicating that it preserves volume but reverses orientation. So it's either a reflection or a multiple rotation problem. In this case, we can see that it's a rotation described by rotating around 90 degrees around the E1 axis, followed by rotation around the -90 degree axis around E3. So I can view it as taking this matrix, filling in 90 for alpha, this matrix filling in -90, multiply it out, you'll see you get back that solution. If you couldn't see how to get there, again, as you take a bunch of examples, you want to make sure you take enough that you can figure out the difference between reflections and rotations by sort of seeing where they all go and keeping track of their signs. So the overall matrix A is just the product of those two. So let's now do a problem with a more complicated projection. So let's say that we're given a point with normal n going through the point Q. So here's Q, here's n, and 4 points, y1 through y4. Figure out what are the images of the points yi when projected onto this plane by a perspective projection that goes through the origin. So this is sort of like a standard camera projection through the origin, but this case onto this plane defined by n and q. I will give you a hint up front that one of these points does not do well. It maps to a point at infinity. So work out what's the formula in general, and then work out the specifics for each of these 4 points. Okay, so hopefully you've got your answer now. Let's start with the general formula here. I've adapted it to use y. This is a formula from the book, which is a way of looking at our projection. We just take q dot n, which q and n are fixed here. So q dot n is this dot that, which is just 3 divided by 5 is 3/5. And then for each new point, we're going to have y dot n and then multiply that by y. So for the first point, we get our numerator is 3/5. Our denominator is y1, which is -100, which gives us -3/5 on the bottom times y, which when we multiply gives us 100. So after projection, -100 becomes 100. The point y2 is the one that I give you a hint about. It's not going to work out well. When I multiply y2 times n for the bottom, where I want to do this dot product, I'm going to have y2 dot n is 0, so I get a 0 on the bottom, which gives me a point at infinity. For the points y3 and y4, I'm going to take their vectors dot n, and the first one gives me -4, -4/5, which gives me an overall vector of 0, 0, 3/4. The y4, when I dot this one, I get 4/5, so I get the point 0, 0, 3/4. Notice these 2 points are exactly the same, even though y3 and y4 are different. That's true for all perspective projections. There's infinitely many points that project onto the same point. So there's always some maps that are overlapping. Let's do another one where we want to find the affine map. This is a little bit more complicated. So given these 4 points, x1 through x4, and the 4 points y1 through y4, find the affine map that maps these 4 points into those 4 points. So x into y, map them. Remember, it's a full affine transformation. Come back after you have your answer. So one part of the affine transformation is just to look at the translation, and so we can sort of say, okay, I want to translate x1 to y1. Well, we'll use as our translation elements. The more difficult part is figuring out what's the map. And from the book, we know that the map A is given by y x inverse, where x is each of the points where we subtracted off x1, our base for the x coordinate system, gives us this column vector. So we have 0, 1, 0, minus 1, 0, 0. That's our first column here. And then so on for x3 minus x1 and x4 minus x1. Y is similar. We take y2 minus y1, y3 minus y1. And the x1 and y1 are our base points we're going to use for determining our translation in the next slide. So now I have this 3 by 3 matrix. I can go ahead, use Gaussian elimination or one of our other techniques to solve that, find its inverse. So here I have its inverse. And then I can just take A is equal to x times, y times x inverse, which gives us that A is equal to minus 1, 1 down the diagonal and zeros everywhere else. And our overall affine transformation is x minus x1. So you take a point x from the x space, subtract x1, multiply by A, and then add y1, and that gives us our final point. If you want, you can take that matrix back, check it by taking a bunch of the points and checking to see that they map to each other. It's always good to check that you haven't had an algebra error. Okay, let's look at another problem. Now we have a homogeneous transformation. So this is a 3-dimensional problem represented as our 4 by 4 homogeneous matrix. Given x1 multiplied by this matrix, this one does not have a projection, so write this one as an affine transformation. What's the equivalent of affine transformation? Okay, so seeing the affine transformation, we can just remember that since we're pre-multiplying here, our matrix has a scaling and rotation matrix in the upper 3 by 3 matrix. Our translations are along the right-hand side and the projections are along the bottom, so we get our point P1, P2, P3. So I can just basically chop out the upper 3 by 3 matrix times x plus the column from here, 1, 1, 0, gives me my overall affine transformation. Given an affine transformation, I could put it into homogeneous by just shoving these items back into the right elements. Okay, so one last one. Now we're going to go through doing a projection given the points P, Q, and R. What are the projections of these points if they exist when we map them onto the plane x3 equals 1, and again we're going to do the projection through the origin. So work out what that is. So again, we can look at this 2 different ways. I can look at a 4 by 4 matrix. These come from equation 1010 of the book if you wanted to go look them up. Hopefully you already know where they come from. So this upper 3 by 3 matrix is just the identity matrix times q dot n. And the bottom right-hand scaling is x dot n. That gives us our projection, some of our projection elements. In this case, we could also write x prime in the same kind of formula we had when we did the triangles just a little bit ago. Now, when I'm doing this, I have to figure out what is n. So n here, I want to project onto the plane x equals 1 from the origin. So I'm going to take 0, 0, 1, x3 equals 1, minus the origin. So my normal is the vector 0, 0, 1. And q, and note this is a different q than the one that shows up here. Just because the letter gets used in a formula in the book doesn't mean it has anything to do with the ones that shows up in our problem. So in this case, q is a point on the plane, which in this case I'll say is just 0, 0, 1. Thus, q dot n is 1, and x dot n is just the third component. And projection is really just dividing these by the third component. So we get 0, 1 half, 1. Right? We divide it by 2. In this one, we get 1, 0, 1. We divide it by 1, nothing changed. For r, we'd want to divide by 0. Not a very good thing. Can't divide by 0 gives us a point off at infinity, so we can't really solve for r. It's a point off at infinity. Okay, that's it for our practice problems on some of these projections. Again, if you had to struggle with these formulas, if you didn't see where these things came from, or you had to keep looking them up, I recommend you go to the back of the chapter, take some of the practice problems there, and work through them.